Let's attempt some multiple choice questions from an exam standpoint on determinants and matrices. I think the examination is in the first week of Feb, so we have 1 week to prepare. So I've just shortlisted top 23 questions, which kind of comprises of the whole of syllabus on determinants and matrices for the Maharashtra State Board first year diploma. So let's give it a shot. And as a precursor, I've also uploaded roughly 18 small bite-sized videos on the crash course on matrices and determinants. I strongly recommend that you guys go through that first and then attempt this. It will be much easier. Much of the problems and solutions have been drawn from that, so it will be easier for you to relate. And we will see when we cross-reference some of the solutions back to that. So let's jump into solving our top 23 MCQs on matrices and determinants combined. Okay. All right. What is the first question? Order of a matrix or a determinant is given by, and then you have got four choices. And if you remember, what is the order of the matrix? Let's say if you have a matrix like this, and let's say you have 1, 2, 3, 4. So order of the matrix is nothing but we have to just count the number of rows and the columns, and anything that is in the x-axis is rows. So this is row 1 and row 2. And anything that is parallel to y-axis is column 1 and column 2. And you always write the number of rows followed by the number of columns. So it's number of rows by columns. It's not multiplication, it's like almost rows by columns. Okay. So let's see what answers suits us. Order of the matrix or determinant is given by columns into rows. Nope. Columns, rows into columns. Yep, this is your answer. I don't think we need to go any further. What it says, rows plus columns and rows minus columns, those are relevant. So order of a matrix is rows by columns. What is the next one? A determinant is valid or applicable only for, and we got four choices: rectangular matrices, row matrices, column matrices, or square matrices. So determinant is a concept that is derived from matrix, and when it is applicable, if you recall from the geometric intuition, we think about determinant as some transformation in space where we have a square object and then it reduces or scales up. So we know that we need to have coordinates in a two-dimensional plane, or if it's a three-dimensional plane, then it becomes more of a cube or a parallelepiped. We have also seen that in our this thing. So what is the determinant valid for? Determinant is applicable only for square matrices where the number of rows is equal to number of columns. It has to be square matrix. For example, let's say 1, 2, 3, 4 is a square matrix, whereas 1 and 3 is not a square matrix, it's a rectangular matrix. So determinant is only applicable for this kind of matrices, a square matrix where the number of rows and columns are kind of the same. Okay, let's move on. A unit or identity matrix is a matrix which has, okay, what is a unit or identity matrix? Okay, we know that if we just take example of a square matrix, unit or identity matrix is a special type of square matrix where all the diagonal elements, the principal diagonal, are 1 and remaining elements are 0, and it's called as unit or identity matrix. So let's say which answer kind of fits this description the best. All elements as 1. I don't think so. We don't have all elements and 1. This is not the answer. First row as 1. First row also is not 1 because its first row is 1, 0. This is not the answer. Diagonal elements as 1. This is the diagonal element that has 1. This looks like to be the answer. Okay. And the last one is first column as 1, and that's also not the true answer. So a unit or identity matrix, the matrix where all the diagonal elements are 1. A scalar matrix is a matrix. The next question, question number 4. A scalar matrix is a matrix which has, okay, how do you think about that? If you remember, scalar matrix is also a type of square matrix, and even a unit matrix is also a scalar matrix. And what is scalar matrix? Scalar matrix is nothing but something of this format where all the non-diagonal elements will be 0, and you will have something over here, and whatever is this number, it will scale up or scale down the given input by that. For example, let's say if you have this square, and if you want to convert this square into a square which is twice the size, okay, then we need to apply a scalar matrix. And since we need to double the size, we will use this kind of a scalar matrix where the diagonal elements are 2. So when we apply this transformation, or when we apply this matrix multiplied by this coordinates, the effect will be as if the whole square or all the coordinates within that has been scaled by twice. So we know that a scalar matrix is a matrix, and let's check out the options. All elements as non-zero, that's not true. That principal diagonal elements are same and non-zero and other elements are zero. This looks like to be the answer, where you have principal diagonal elements as same and they are not zero and remaining elements are zero. Let's go through the other answers. Both diagonal elements are same and other elements are zero. That's not true because the other diagonal has zero elements and all elements as one. All elements cannot be one. So it looks like this is the answer. Principal diagonal elements are same and non-zero and other elements are zero, kind of a thing. That's a scalar matrix. Okay, what is a square matrix, which we already kind of discussed about? A square matrix is a matrix which has anything that has same number of rows and columns is a square matrix. For example, we have 2 rows and we have got 3 columns. Similarly, if I add one more, 7, 8, 9, 1, 2, this is a 3 by 3 matrix, again 3 rows and 3 columns. So we know that a square matrix is a matrix which has the same number of rows and same number of columns. We don't have to go any further. This is the answer. We know that. Okay, and other answers are not even valid. If you see, number of rows is a square of number of columns, not true. Number of columns is a square of number of rows, not true. And all elements are square of an integer, that's also not true. Okay, question number 6. Matrix A and B can be added only when? Okay, when can we add two matrices? Okay, we have, let's say we have this, let's say 1, 2, 3, 4, and then we have another matrice 5, 6, 7, 8. Okay, when this can be added or subtracted? Whenever the order of the matrix, this matrix is a 2 by 2, meaning it has got 2 rows and 2 columns, and this matrix also is a 2 by 2, meaning it has got 2 rows and 2 columns. Whenever the order of the matrices, both the matrices which are trying to be added or subtracted are same, then only we can add. For example, if the order was not like this, let's say it was like this, where the order is just 2 rows and 1 column, then we cannot add it. So what does it mean? The order has to be same. Let's check out the choices. Both matrices have positive elements, not true. Rows of A matches columns on B, not true. Columns of A matches rows on B, again that's not true. Both A and B have the same order. Yep, hands down, this is the answer. Okay, because we need to have the same number of rows and columns, which means both the matrices A and B will have the same order, which is 2 by 2 in this case. Okay. Okay. Matrix A is of order 3 by 2 and matrix B is of order 2 by 3. A multiplied by B, matrix multiplication, and we have got choices. Is possible, not possible, and what happened? So let's recall quickly what it means. So let's say we have a 3 by 2 matrix and then we have a 2 by 3 matrix. Okay. So let's say we have A and we have B here. And what is a 3 by 2 matrix? Let's say we have got 3 rows and 2 columns. So we have got 3 rows like this. So, and we have got 2 columns like this, right? So 1, 2, 3, 4, and 5 and 6. So this is 3 rows and 2 columns. And what is matrix B? Matrix B has got 2 rows like this and 3 columns, 1, 2, and 3. So let's fill it out. Okay. So this is what is matrix A and B. So when is this multiplication possible? A multiplied B. If you remember in one of the crash courses, if you saw, we are clearly told that we have to check these 2 closer numbers. Once you write the order of both the matrix, these 2 numbers should be same, which means the columns on matrix A on the left side, left matrix, the columns on this matrix should match the rows on the matrix B on the right side, or the 2 inner numbers should match. Then only the multiplication is possible. If the numbers are different, then multiplication is not possible. So let's see what is that we have. So in this case, is multiplication possible? Yes, it's possible. So the first answer is not true. Possible because rows of A matches columns on B. So rows of A matches columns of B. That's not what we're looking at. Possible because columns on A matches rows on B. Okay, let's read it. Columns of A. Okay, columns of A is this. So columns of A matches rows of B. Yes, this is our answer because that's what we're trying to say. Because the columns on the left matrix should match the rows on the right matrix. And the last answer is possible because both are rectangular matrices. That's not true. Excuse me. So we have that answer as C. Okay, matrix A is of the order 3 by 2 and matrix X is of the order 2 by 3 and we have AX is equal to B, that means we are multiplying two matrices to give the B, the order of the resultant matrix B, the output matrix, what is the order of that? So it's the same example over here we can say. So we have got 3 by 2. So for the multiplication to be possible, the inner numbers, which is the columns on the left matrix, should match the rows on the right matrix. And once you multiply this A and B, or in this case A and X, in this case it's a X, right? This is A and this is X. Once you multiply, whatever is the output matrix, the order of that matrix will be whatever are the remaining two numbers, this number by this number, meaning rows on the left matrix, which is 3, and columns on the right matrix again, which is 3. So this will be the order of this matrix once we multiply this. So this matrix will have 3 rows and 3 columns, 3 by 3. Is the 3 by 3 answer over here? Yeah, we have a 3 by 3 answer over here. So that's MCQ 8. Let's move on to 9. When rows and columns are interchanged, what do we get? So when rows and columns are interchanged, for example, let's say 1, 2, 3, 4, and we interchange the rows and columns. What does that mean? Row becomes column and columns become row. So first is row is 1, 2, it will become column. Second row is 3, 4, it will become column 2. So this is what it's interchange over here. Rows and columns are interchange. So whenever they are interchange, what we get is a transpose of a matrix. Okay, we get a transpose of a matrix. When rows and columns are interchange, we get a transpose. We don't get inverse, definitely not minor and not scalar. Transpose of a matrix. Okay, a determinant of a matrix can be only positive, can be negative, cannot be 0, can be any number, positive, negative, or 0. Okay, we have seen what is the determinant. Let's say we have a 2 by 2 matrix and let's say we have A, B, C and D. We know the determinant is cross multiply AD minus BC. You first multiply this diagonal, multiply minus the elements on this diagonal. Okay, AD minus BC. And if you recall, we know that a determinant is just a number and it can take a positive value, it can take a negative value, or it can be even 0. We know that. And hence D is the right answer. It can be any number, it can be positive, negative, or 0. Determinant of a matrix. Okay. All right, let's solve this example here. Determinant of a given matrix is same story here. We saw that we have to just cross multiply the diagonal elements AD minus BC. So we first multiply this diagonal, which is 1 into 4 minus, then we multiply this diagonal 3 into 2. And what does that give us? This 4 minus 6 is equal to minus 2. Is minus 2 an answer? Yes, minus 2 an answer over here. That's the answer. Okay. Now let's take a 3 by 3 determinant. Determinant of this matrix, which is a 3 by 3, what is the answer? And if you remember, for taking the determinant, we can take any row or any one column, and then we have to find the minors of that, which in case, I think I'm solved it down. Let's take the problem down. This is a solution I've copied. This I've used in the crash course, so I've just copied it. If you see here, this is a given matrix and we're trying to find the determinant, and they're trying to find the determinant using the first column. We can take any row or any one column. They're trying to take the first column. So if you see here, we have 2, then we have 0, and then we have plus 1. And if you remember, we have to alternate the signs. We start from plus here, then minus here, and then plus here. And we take the determinant of the submatrix. So whichever row has this element 2, first we start with that. We should ignore that row and that column, and whatever is remaining, we'll take the determinant of that, and so on and so forth. And when you solve this, we get the answer as 21, and that means we have to find if 21 is a part of the given answer, and if yes, that's our answer. Let's go back to the problem. Determinant of this problem is the answer 21. Yeah, that's the answer is 21, and I've solved this in the crash course, and you can refer to that. Otherwise you can solve it yourself, but that's what it is. Okay, let's move to the next concept. Minor of an element. Okay, we have a given matrix where they have given in terms of subscripts. If you remember, the first subscript is the row. If I say A11, it's the first row and plus first column combination, that is this. So we're asking the minor of element A22. So A22 means this element over here. So that means second row and second column. What is the element? So whatever this element is, this element, what is the minor of that? And how do you calculate the minor of the element? We will just ignore the row and the column this element is present. So if I ignore this row and I ignore this column. So whatever is remaining, I should take the determinant of that, and that will give the minor of this element. What is remaining in the same sequence? We have A11 from here and A13 from here. And then we have got A31 and we have got A33. And if I take this determinant, whatever determinant I get of this by cross multiplying, that will be the minor of A22 or second row and second column element. And let's see if we have an answer matching to this. So we want something that matches this, and looks like this is our answer over here. A11, A13, A31, A3, and remaining are different. So that's the minor of the element. Okay, now another concept, cofactor of an element. So we know that cofactor of the element is nothing but once you find the minor, and when you assign the signs plus or minus, it becomes the cofactor. So let's try to find here. So the cofactor of the element A21, that means second row. We're talking about second row and first column, that is this element. What is the cofactor of this element? We are trying to find that. So the cofactor of this element, for that we need to find first the minor of this element, and then we have to apply the right plus or minus sign to get the answer of this. And I think I've solved this problem here at the bottom. And again, it's copied from one of the exam. I think this is one of the exam problems that came in one of the years, and I had solved it in detail. So it's the same thing that we are going to solve. Okay, so what is this? This is the answer here. So we're talking about, first we have to find the minor of the 3, which is that element that we're talking about. This element is the second row first column element, and we are taking this minor over here. And if you remember, minor is nothing but the elements that is left over after deleting the row and the column. So if we are trying to find the cofactor of this element, so ignore this row and ignore this column. Whatever is left, you take the determinant of that, 1, 1 and 5, 1. Okay, so 1, 1, 5, 1 is your determinant here. The same thing you will see here, I think. Okay, let's go here. See, 1, 1 and 5, 1, and then you cross multiply this. 1 into 1 is 1 minus 5, so you get minus 4. Now that's a minor. Now we have to convert this into cofactor, so we have to apply this cheat sheet on this thing. So we are trying to find the minor of this element, which is in the second row and first column. And whatever value we get as a minor, we have to do the opposite of that. So because there is a negative value, it's like multiplying it by minus 1, right? The opposite of that. That's a definition of cofactor. So since we have minus 4 here, we take minus 4 and which almost multiplying by minus 1, or we are negating this. This gives us plus 4. The answer should be plus 4, and that's the cofactor of that element in that particular position. And let's see what we have. So do we have a plus 4? We definitely have a plus 4 here. This is the answer. Okay, let's move on. Find the adjoint of the matrix. Okay, now we have got this, we have given a matrix here, and we have to find the adjoint. And we know that adjoint of the matrix is equal to transpose of cofactors. Transpose of cofactors, and this cofactors itself is nothing but matrix of minors for all the elements, and then you sign them with alternating plus or minus that we have seen. So let's take this example, adjoint of a matrix, and they are given us the possible answers, and let's see which one matches. I think again this was solved in our crash course, and I think we'll just copy that and use that over here. Let me check where it is. Just 1 second. Adjoint of the matrix, right? Okay, here is a problem. Okay, so this was one of the examination problems that we tried to solve, adjoint of the matrix, and this came in one of the exams, and I've solved. So what we have done is, since it's a 3 by 3 matrix, there are going to be 9 elements. The first thing is, like I've written here, transpose of a cofactor matrix. Then cofactor itself is a matrix of minus with alternating plus or minus sign. So what we need to do is first find the minors. And since we have 9 elements in this matrix, there will be 9 minors. We'll take one row at a time, and within that row we'll take one element at a time. Okay, and then find the minor. If you see all these things in orange are nothing but the minors. Eventually we'll have 9 minors and we'll form a matrix of minors this way. Okay. Now we have to find a matrix of cofactors, which means we have to apply this cheat sheet of alternating plus or minus sign to this matrix, where the diagonal elements remain as it is without any change of sign, and the non-diagonal elements, which is highlighted in the purple color, that will have the opposite sign, whatever was in the minor. And once you do that, you get this kind of cofactor matrix. And then to get the adjoint, you take the transpose of this matrix, which is interchanging rows and columns, and then you build this matrix. For example, if you take the transpose of this, the row becomes the column, and this is what you get. So whatever is the answer, which will be in this format where it's -1, -3, 1 and 7, and ending with -13. And let's say we have a answer in that format. Let's try to see that. Okay, do we have an answer? Okay, we have an answer in the form of B. It looks like it's matching over here. We have -3, 1, 7, and then we have -13. I think that's the answer. Let's double check that. Last row is 5, 1 and -13, right? Last row is 5, 1 and -13. Yep, that's the answer. So adjoint of the matrix, that's how you find it. Now the next question on MCQ 16. Determinant of a matrix can be computed using, okay, let's see, using diagonal elements, using the first row, using the first column, or using any row or any column. So we already done this in example. So let's say we have a determinant, let's say A, B, C, D, E, F, G, H, I. To compute the determinant does not change. You can take any row. We have got, this is a 3 by 3 matrix. We have got 3 rows and 3 columns. You can take any of these 3 rows, any one, or you can take any of the 3 columns, any of this one. So the determinant does not change. So we have the option to choose any row or any column to find the determinant, and looks like option D best fits our answer over here, any row and any column. Okay, again, this is one of the examination questions, I think. Find the area of triangle whose vertices are this. So we have got 3 vertices given by the triangle. Let's say this -3, 1, and this 1, -3, and this 2 and 3. And we know that area of the triangle can be found by using the determinant formula. And let's try to apply that. So what is the answer on this one? So let's try to apply the area of the triangle. I've solved in detail this example while explaining what is the formula. We applied this formula where we take plus or minus half, and we take the determinant, and the first column is full of x values, the second column is full of y values, and the third column we just pre-fill with number 1, and we solve this determinant. And to make sure the answer is positive, if this determinant is negative, then we just force it by using this negative sign and make it positive. And if this is positive, we leave it untouched, and we have to finally multiply it by half and make the final answer as square units. This was a long explanation, but if you see the determinant formula I have solved at the bottom in this example over here, I have taken the determinant as a 3 by 3, and in this case I am going across the first column. The first column, I'm taking the determinant across the first column, and what I'm doing is taking one element at a time and taking the minor. If you see this, and this, I'm taking one element at a time in this column and calculating the answer. And once I finally get the final answer, okay, where is the answer? Okay, it should be here. Okay, here it is. Area of the determinant using determinant, we take this answer, and once I solve for this, I get an answer as, if you see here, my answer is -14 here, but area cannot be negative, and hence I take the example and apply the negative sign. Negative becomes positive, so I force the answer to be positive. So the answer is +14, and we should not, we already used the half here, so don't discount that half. Normally we forget. So the answer is +14, and we always need to mention the square units. If you don't get square units, you will not get the mark on that one. So the answer is +14 square units. Okay, and remember the trick where we applied the plus or minus negative sign to apply this formula. So this was the area of the triangle. The answer is +14 square units. Okay, now the question on a Cramer's rule. Solve for y. So these equations, we have got 2 equations, and this is called as simultaneous equations or system of linear equations. We have got 2 equations, and we have got 2 unknowns, and we know that we can use Cramer's rule as one of the methods to find the value of unknowns y. In this case, they're asking you to find the value of y, and we know Cramer's rule for the value of y. The value of y is equal to dy by d, and we know what that means. And we have this example also we have solved. Now let's take the solution from the crash course which I applied here, and let's solve this. So this is Cramer's rule. This is a given equation. In this case, we have solved for both for x and y, but we are interested only in y in the MCQ. And the first thing you need to do is, it's a ratio of ratio of determinants, sorry, if you remember Kramer's rule, it's a ratio of two determinants. There's a determinant in the numerator by dy, and there's a determinant in the denominator by d, which is nothing but the determinant of this coefficient matrix. If you see here, first we find the determinant of the coefficient matrix, and the answer should not be 0, because if the denominator becomes 0, the solution will not exist. So the answer should not be 0. Here we get 3, this one. And then we find the numerator, which is nothing but this, where you try to replace the y column. This column gets replaced by the constant 4, 2 over here in green. X remains as it is. X is 1, 2 over here. It remains as it is. And then you find the determinant of that, which is -6. And then you take the ratio of this determinant over this determinant, which is what these people are doing here, -6 by 3. The answer is -2. So the value of y is -2. That's how you solve the Kramer's problem. Okay, -2, right? Let's see whether we have an answer. Okay, the ratio of determinant is -2. Okay, let's move on. Okay, what is this question? Okay, 3 points. Okay, sorry, question number 19. 3 given points are collinear if and only if. Okay, what does that mean? So we have got 3 points, and collinear means they're on the same line, A, B, and C. And this is again one of the applications of determinant, where we have got 3 points and they're collinear. And if you know, they're collinear only when, what is the condition? The determinant is positive, determinant is 1, determinant is 0, determinant is less than 1. So the answer is determinant should be 0. If you remember, we have done this in the example where we take all the 3 points, and it's the same formula as the area of the triangle, but we don't apply the plus and minus half. We just take the simple determinant, where we say we take all the points here. The first column will be of all x values, second will be of all y. For example, this point is x1, y1, and x2, y2, and x3, y3. So we take all the x variables, all the y variables, and this is unit. And in the area, normally we apply plus or minus half, You don't have to apply that. You just need to take the determinant of this. And if the determinant is 0, that is enough to prove that these 3 points are collinear. So determinant should be equal to 0. That's the formula, and that's what answer C is pointing to. That's what it means. Okay. Okay. So let's see. Okay. Let's see the next problem. Okay. 2 matrices are inverse of each other. Okay. 2 matrices are inverse of each other. They're talking about inverse. If the product of these matrices is a, okay, what does that mean? What are the options? So let's say that 2 matrices. Let's say we have A and we have A inverse. Okay, we have got 2 matrices, and we are taking the product of that. So we are multiplying it. So if these are inverse of each other, what should be the output? That's the question. What is the output matrix? Is it going to be null matrix? I don't think so. Null matrix means all the elements are going to be 0. I don't think so. Is there going to be unit matrix? Unit matrix is nothing but identity matrix, where the diagonal elements are 0, and this is also called as I, or identity matrix. And looks like that's the answer. When 2 matrices are inverse of each other, the product is I, unit matrix. I think that should be the answer. But let's check the other answers. Has 0 determinant? Not possible. Has negative determinant? That's also not possible. So unit matrix or identity matrix, that's the answer over here. So 2 matrices of inverse of each other, A into A inverse is equal to I. If you remember that, that's how it proves the inverse of a matrix. Okay. Now let's take another example. So again, it's the inverse of the matrix, but with this time we have numbers. So we are given as a 2 by 2 matrix, 2 rows and 2 columns. Inverse of this matrix, which is 4, 7, 2, 6 is what? And if you remember, the inverse of a matrix is given by the formula A inverse is equal to 1 over the determinant of the original matrix, this matrix, multiplied by adjoint of A. That's how it is given, right? So we have to, and it's a long process. We have to find the determinant of this, and then we have to find the adjoint of this, which we have found, and then we have to apply. And let's see, I think I've again solved this problem somewhere. Let's see if I can get that problem here. Okay, I have it here. At the bottom, I put the solutions for quick reference. And this again was solved in one of our crash course videos on inverse of matrix. So what does it say? So A inverse, this is a formula for 2 by 2 matrix. So they have taken this. So 1 over the determinant. So as I mentioned, it's 1 over the determinant multiplied by adjoint of the given matrix. That's the answer. So this is the 1 over the determinant, this part, and this is nothing but adjoint of this matrix, which is you take the matrix of minors, then you take the matrix of cofactors, and then you take the transpose, then you'll get the adjoint. And once you solve this, you get 1 over 10, 6 minus 7 and 2, 4, or you can simplify this. So this is your answer, right? And let's see if there is any answer it matches in this format. Let's go back. Okay, inverse of a matrix. Okay, so looks like answer D matches, where we have 1 over 10 and we have the rows 6 minus 7 and minus 2 and 4. 6 minus 7 minus 2 and 4 and 1 over 10. So that's the answer. That's how you find the inverse of a matrix. Okay, question number 22. A matrix cannot be inverted, meaning the inverse does not exist. What are those matrices called? That means we have got A and we have got A inverse. But we know that for all matrix A inverse does not exist. It exists only in certain cases. For certain cases, it does not exist. And whenever it does not exist, that's called as a singular matrix, because it's an exception. We are singling that out. Singular matrix. Okay, over here, it's a singular matrix because we're singling that out, and this matrices cannot be inverted. So A inverse does not exist for this kind of matrices, and that's what it means. And let's take the last question for the MCQ. For non-singular matrices, what happens? So that means, let's say when you say non-singular matrices, that means we have a matrix A and the A inverse exists. Okay, that means that's what non-singular matrices are. For non-singular matrices, what happens? Determinant is always 0. I don't think so. Determinant is non-zero. Potentially yes, because for non-singular matrices, since it's invertible, the determinant is going to be non-zero element. It will exist. Okay. Other answers are determinant is always positive, determinant is never 1. So I don't think any of this matches. So the test for singular and non-singular matrices, you find the determinant. If the determinant is equal to 0, then it becomes singular. And if the determinant is not equal to 0, then it becomes non-singular. That's what the definition is, where there is no inverse existing in this case, and over here the inverse exists. That's what it means. So the answer is B, determinant is non-zero. So I think that's a quick wrap up on all the important questions that you might potentially get on the syllabus of matrices and the determinants. I think if you solve this, you don't have to worry. And like I said, always go through the crash course first and solve this. It will be easier for you to apply. And I don't think you're going to get any questions out of this, because it covers pretty much all the concepts. And there are some beginners level, intermediate level and advanced level questions which can be tricky and you'll be able to solve. And since all the questions are going to be for 1 mark each, I don't think you can expect any questions for which you need to solve in a lengthy way to get 1 mark. It is going to be pretty much straightforward or a short answer. So I think that should be good. So that should be a good refresher for you for MCQs on determinants and matrices. I'll see you in the next episode on some different topic.